Mark Benton. I'm a senior principal development engineer at TE, and I'm part of a team of advanced systems and architecture folks who kind of look at systems on a holistic basis. And I'm going to talk to you a little bit about active optical transceivers and why modularity will help you in solving some of those system problems. So we're going to touch on some examples of systems where this modularity can be useful. I'm going to introduce you to a technology we call a light engine platform and go through some examples of how that led to marrying that technology to the electrical abilities of multi-gig RT2 and resulted in a transceiver capability. Talk about the product platform that's going to evolve from that, and then take you into some future applications of things that we see on the horizon, both for that platform, but in terms of other ways you can use this technology. So if you look at systems that need modularity, if you think about the datacom world, you'll often find a large switch box with lots of transceiver ports on them. You populate those out as you need them. Well, in some of our markets that TE serves, you've got in-flight entertainment. And if you look at that system, you basically have all of the media and the content that's stored on your file server, and you have the KSAT connection to the airplane. You've got a few inputs, but you may be servicing anywhere from a few Wi-Fi points and tens of seats, depending on the size of that airplane, or you may have hundreds of seats and tens of Wi-Fi points to get all the connectivity you need for that system to work and deliver the content to the users. Another example you run into that has unbalanced inputs and outputs are things like display support equipment, where you have multiple inputs, but you've got a fixed number of destination points. You've only got 4 or 5 displays. So you may have active real video, you might have radar, you might have geography and map information that needs to get processed and overlaid and then delivered to those screens. Here's a system where you've got a lot of inputs, but only a few outputs. So in an optical network, that's an unbalanced system. So you want the ability to match up your solution to that system. So let's talk a little bit about what we call a light engine platform. And this is a technology that came out of our corporate development group about 4 or 5 years ago. It was actually aimed at automotive at the time, and we've adapted it to this market. If those of you who aren't familiar with that, the image on the screen is one of those datacom pluggable transceivers. It's called an SFP Plus. That's basically a 10 gigabit device. It's got 1 transmitter and 1 receiver in it. And it's about the size of my index finger. So if you look inside that transceiver, what you find is you've got a transmit circuit, you've got a receive circuit, and you've got some health monitoring, which I've got the little do not include dot on. We'll come back to that later. But you look at what's important inside that transceiver, you can take that transmit circuit and mount it on a piece of ceramic that's a couple of millimeters square. You can do exactly the same thing with the receiver. Well, why is that important? Well, it's important because if you look at those two things and you take a look at them, I just put that transceiver on the tip of my finger, okay? Well, once I've got that on the tip of my finger, the question becomes, how does that benefit me? What can I do with that kind of a building block? Well, let's take a look at some examples, okay? So you've got your building block on your finger. I can take one of those 2 engines and I can put that behind a fiber optic contact, build it into a receiver, and make myself a transceiver right on the panel of a box. So instead of running fiber into my box, I run electricity into my box. The conversion happens in the contact. Or if I have a case of a system where I have a certified LRU, flight certified, I can't take it apart, but now I have them far enough apart, I need an optical link. How can I solve that problem? Well, I can put the transceiver or the conversion in the back shell of my cable assembly, turn that cable assembly into active optical. So think of a rugged version of a datacom AOC. Or I can take that engine and put it back in that SFP housing, but this time I need to submerge it 6,000 kilometers, you know, six kilometers down in the ocean, and I've got to resist that pressure. Well, you're not going to use the internals of that transceiver I started with and pull that off without crushing it, frankly. So that's some of the examples of what you can do with it. So we started out with a little transceiver we fondly called the Redwing at the time, and started talking to customers about how they could use this. And as I said, since we can put this wherever it makes sense and it's modular, where do we go with this? So we started talking to some customers, and lo and behold, we ran into an IFE server situation on an aircraft where, much like that datacom switch, I had to be able to modularly add transmit and receive channels to that box. It had to be anywhere from 1 to 10. It had to be 1 gig to 10 gig, depending on how much traffic and how far they were pushing it through the airframe. Well, that was great, but even at a 1/2 inch square, a dozen of these transceivers didn't fit in the system, the customer's available space. The design development guys that were working on the light engine at the time were also familiar with multi-gig RT2, which is a wafer-based backplane electrical connector. And you might say, well, why does that matter? Well, it matters because RT2 is a proven, rugged, been in the market, this market since 2005, I think, 10 gigabit differential electrical interface. We know it's rugged, we know it's easy to install on a board, and the connector is actually circuit board based. Well, so now what happens is the science project that you see at the bottom, where you basically took those optical engines and mounted them on one of those circuit board wafers, you now have a 10 gig transceiver, okay? So that becomes, with a lot of work and effort on the part of the design team, ruggedized well enough with the appropriate hardware so that now when you install this in the middle of a system and run fiber pigtails to, say, the output on your box, you've got resistance so you don't pull these things out of housings and what have you. And it's modular because you can attach just about any type of fiber optic cable that we use in this industry, or any of the fiber optic contacts that we use in this industry, and then add them to housings that can be from 1 slot to a dozen, and populate your system as you need to do it, okay? We also found in talking to customers that even in this case, they had height constraints. So we created a version that was just a single fiber transmitter or receiver for those situations. So this summary of the product line just popped up on the slide. We've been shipping this to our development partner customers since about 2022 now. It's primarily been commercial air, but there's one VPX application I'll show you in a second. It's capable of running anywhere from 20 to 10 gigabits per second. It's a multi-mode system. Most of these platforms are small enough that you don't need to be, and don't need the distance you can get out of single mode fiber. It's a very low power distribution. Because of the way the fiber gets coupled to the devices, you can build a 10 gigabit transceiver and only have about 130 milliwatts of power consumption. That's important because it comes back to the optical efficiency of the coupling, and the lower that power is, the lower the currents on your lasers are, the better your reliability is going to be over the lifetime of the system. It'll run from -40 to 85, and it's been tested to most of the applicable standards, either from the commercial aviation space or VITA in the military markets that we've been involved in. The platform that goes to market is literally parametric based, so you have the different styles of blades that you can have. There's 2 speed ranges, up to 4 gig, which covers a lot of the commercial aviation applications, and up to 10 when you have to handle Ethernet. Anything in green on the chart you see here are things that we're shipping today. Anything in yellow is on the roadmap, which we're going to talk about in a bit. As I mentioned earlier, there's a whole array of fiber capability that you can tie to these engines. Because you have different heights, you can manage the space requirements that you have. And in a larger assembly housing that's using those RT2 pins, you can mix and match different styles. So you don't necessarily have to have transceivers. You could have dual transmitters. We have one customer that is feeding displays, and they literally just have 2 dual transmitters. That's all they need for that particular application. You've got length as a variable, of course, and then last but not least, as I mentioned earlier, any of the rugged fiber optic termini that you typically use in this industry, you can put on those cable assemblies and then install them in whatever panel connector you have. And in some cases, for certain customers, that entire thing becomes a ship set, the connectivity that's mated to the end of the system as well. This is a VPX example that we use to help a customer save some space. And so you have a 3U card with a VITA 66.4 connector on it. It happened to be a system that had 4 dual receiver, single mode receivers on it as the end of a sensor processor. And when the customer looked at that, that was a lot of space, and they were really kind of concerned about it. So when you replace that with the equivalent 8 receivers in this platform, you can see what happens to the space. You can see it here tied to the single mode APC MT connector that works in the VITA 66.4. That turns out to be about a 70% space reduction on that card, replacing those COTS parts with this technology, and it's a lot simpler harness to manage. You don't have a fan out to 8 LCs, which are, you know, 3/4 of an inch long, hanging out of those transceiver ports. It became a really, really efficient solution for the customer. So let's talk a little bit about where we see this going and what capabilities we know we need to add to this based on other applications. One of the first things we're going to do is extend this further into single mode, because you get certain platforms, things the size of a ship and what have you, where you just can't push 10 gigabit signals far enough on a multi-mode cable. So we're looking at adding higher sensitivity receiver capability on the receiver side, and adding single mode 1310 sources so that we can stretch onto single mode fiber. We're also looking at linear modulation, and by that I mean most of the traffic we handle is digital, zeros and ones. But there are a lot of signals that are tied to systems like radar and what have you, where you have RF timing signals, or you have GPS inbound radio signals that you need to handle. So we're looking at replacing some of the chips on those engines with things that will let us modulate linearly, which now means in some of these assemblies we can mix digital and RF traffic in the same assembly if that's what the system requires. So add another layer to that modularity, as well as being able to mix and match single mode and multi-mode if we need to. Obviously, those of you who've been listening to some of the clock speeds and the data speeds here, a lot of the switches, a lot of the embedded transceivers that are on VPX cards today are already up at 28 gig a channel. So we expect that's going to be coming in our future, so we're looking at how we add that to the engine capability. If you remember the little do not include sign from that SFP at the beginning of the talk, digital diagnostics is important to folks, all right? They want to know what the health of their transceivers are. So we've looked at how do we incorporate that into this chiclet-based transceiver, and as it turns out, RT2 is forgiving, so that in the lower height module, we've got an extra differential pair on that 7-pin array that's the standard RT2 footprint, so we can put the I2C interface right there, and we have identified small enough microcontrollers that have enough memory in them that can literally make this look like part of an SFP module. Case of the full height one, we don't have enough pins, so we're going to need to stretch that mechanical assembly a bit to add some I/O to it, but it's going to use all of the same building blocks that we've already known are qualified in the market, and in that case, we can do that same memory map thing and make that sort of look like a single channel quad SFP. Those software standards are important because a lot of the chips that you run into the transceivers interface with are coming out of the datacom world, and they're expecting to see a certain memory map on a transceiver, and a lot of times that's embedded right in the switch. And so that makes it a lot easier for customers to integrate these kinds of things at the system level, because the switch can manage the transceivers more efficiently. The last area we're looking at is media conversion. This example on the screen right now is video, a lot of uncompressed video that's used in sensors and on aircraft and what have you, and it's got some unique data requirements, but the important thing is you typically need to marry some kind of a protocol chip to do something on the electrical side to get you to the logic level so you can connect it to a transceiver. In this case, it's video, so you've got 75 ohm single-ended, and you need to get into the 100 ohm differential world to connect it to the transceiver. Well, you can literally take the cable drivers and the EQs and put them on a wafer the size of an RT2 wafer, put that in a slot right next to your transceiver, and in a very small space, build yourself a video media converter. The other end of the spectrum we've run into in eVTOL is where you need to reduce weight in the system, so you want to use fiber, but you're running something like CAN bus or serial signal, which is very slow. You don't need a transceiver for that, but you want the ability to get rid of EMI interference and reduce the weight. Here again is another example where you can do a very similar thing. CAN bus ASICs, I think someone mentioned in a presentation yesterday, are ubiquitous. They've been in the automotive world for years. They're readily available and they're very small. You can do the same thing for things like CAN bus and create a media converter solution and add that to the capabilities. And now we're going to come full circle as we wrap up. And so last but not least, remember what we did. We took the light engine technology and we married it to a wafer-based transceiver that had a high-speed interface electrically from a circuit board. Well, where's that RT2 going in the future? If you look at our science project, right, we had a nice little mid-board solution, which was fine, but it's pigtails. You can't do anything with that at the backplane. But multi-gig is evolving, and there's work underway now to double the pin density. So now we've moved up to the point where we've got 4 differential high-speed pins, and in this particular proposal that the TER multi-gig guys are bringing to the VITA standards, you have 4 differential high-speed pairs that are capable of running up to 112 gig PAM4. So you're not talking data rates that you see in commercial transceivers in the datacom industry, and you have 4 differential pairs. Well, if you go back to that same building block idea and you look at what's critical inside a parallel transceiver today, you're going to find quad laser drivers and quad post amps and quad VCSEL arrays and quad photodiode arrays. So you take that same idea that we started with the light engine, you just scale it up by a factor of 4, and now you can look at concepts that we're starting to develop where you can put that on the next generation multi-gig wafer. But this time, we're going to add an expanded beam, smaller MT interface, and a way to make that mateable at the backplane in an embedded system. So now you've pulled a transceiver functionality off the card, say the space, and put it up front on the card edge in connectivity that's going to be there anyway. And so these are concepts that are in development. They're going to take some work. Obviously, the high density multi-gig standards is a work in progress. That's likely to change and morph over time. But just as a size comparison, you can see that a fully populated module concept like this would give you 14 ferrules. That's 56 fibers. So that's 28 quad devices. And you can see the mating backplane that installs the mating side of those optical ferrules so that you've got the float and the mechanical tolerances you need to get that to work in a blind made backplane situation. So I hope that's tweaked your thoughts a little bit. For those in the room that are in the transceiver business, they probably know some of this stuff, but for the rest of you, I hope it was interesting. I'm happy to take any questions at